We're going to spend 2 days on this. Tonight's homework is, I've got a packet for you up here. It's still in this clip, and you'll get it before you leave today. It's the odds. And then tomorrow night we'll be doing the evens. So by the time we're done, you'll find, yeah, for the most part, the examples I'm going to do, I think, are in the packet that I just gave you, though, as notes, kind of. So I think this one isn't, but that's only because it's kind of a little follow-up from the warm-up. This should look familiar. It's basically the warm-up problem. I've got a sphere of radius 10 centimeters. And my question is, how fast is the volume changing with respect to time if the radius changes at a constant rate of 0.1 centimeters per second? Doesn't that feel like the warm-up a little bit? Except for the time piece, right? Except for the time piece, it does kind of feel a little bit like the warm-up. Let's actually write down what we have here. V equals 4/3 pi r squared, pi r cubed, excuse me. That is a true statement about spheres. Regardless of what time that we're looking at the sphere, that is a true statement about a sphere, for sure. But what I'd like to do is have an equation that relates the things that I want to know about in this equation. That is the rates that are given. So in particular, we can start like labeling some things. I think this is like r. But this is not, what does it say? Radius changes at a constant rate. I mean, eventually maybe we seek to, how would we want to write that? 0.1 centimeters per second. That's like the rate at which r changes with respect to time. How would you like to write down a thing called r that changes with respect to something called t? Yeah.
We could have dr times 8.
How about, this is the instantaneous rate of change of the radius. At the moment we were looking at the sphere, we're frozen in time. How would you like to express a quantity r changing with respect to t? The instantaneous rate of change of r with respect to t. Thank you, I guess. No, he's not here.
Okay, cool.
That's all good. Yeah. Yeah, maybe dr dt, if that really is instantaneous rate of change of r with respect to t. Is that what you were going to say, Nicholas? Okay. Likewise, the thing we seek says how fast is the volume changing with respect to time. So the unknown here, we also want to maybe give a meaningful name to. It's the rate of change. This thing we want is the instantaneous rate of change of the volume with respect to time. So what would be a good label for that? Tricio. dv dt would be a great name for that. So notice the thing we know here is an r value, but the thing we know here and the thing we seek to know are both like rates of change. Well, the equation we have currently does not involve any rates of change. It's like a pre-calculus equation. We need an equation that relates some rates. That's why this is, it's going to be called related rates for that reason. We need an equation that involves some rates. So I know how to do that. Do you? There's only like one trick in our tool bag at this point in the calculus class. Yeah, maybe we'll take like a derivative with respect to what? If I want dv dt to appear, then maybe I need to take derivatives with respect to t. It seems like I need derivatives with respect to t based on what you were talking about. So that's what I'm going to do. I'm going to take the derivative of this whole equation with respect to t on both sides. Now, I'll do the hard part for you. The derivative of v with respect to t is called dv dt. There you go. Common guy I am. Now, what about the right side? Keeping in mind that r is possibly something that depends, in fact, it most certainly is something that depends on time. It's a function. We can even think of this as being like r of t. So what is the derivative of 4/3 pi r cubed? We've already maybe thought about it today, haven't we? Yeah.
We can just pull out the 4/3 pi right away, right?
That's true, yes.
Pardon the interruption. Can you send Zachary Bernstein to the main office to sign out, please?
Okay.
Thank you.
Joshua, keep going.
Past that, could we do the power rule and implicit differentiation?
Yeah, I think this idea of implicit differentiation is a good idea. This idea of requiring, I guess the big idea is that we require the chain rule in order to take the derivative of r cubed with respect to t, that's not r, right? Like if I were just taking the derivative with respect to r, I think we'd all say, oh, this is 4 pi r squared, and be like done with it. But wait, hold up. That's the derivative of this side of the equation, true, with respect to r, right? But what's the derivative of this expression with respect to t? Well, it's the same thing times dr dt. That's called, if you didn't know that, that's called the chain rule, okay? That's called the chain rule. So this is critical, and I want to make sure you just caught what happened there. Or again, if it helps you could write this as, v of t equals 4/3 pi r of t cubed. Just to remind you that, I don't actually recommend doing that, but just right now at least, just to remind you that what we're dealing with here are, v and r, maybe we can think of them as being functions of t that depend on t. So, good. Now, if you believe all this, then we're done, kind of, right? Just plug in the things we don't know, find the thing we need, whatever. Plug in the things we know, find the thing we don't know. 4 pi, what is r? 10. By the way, does this look familiar at all, the equation above what I have written here? Actually, you know what I'm going to do? I think at this point in my life, I would like to include units as I do this analysis, just because I think that would be fun. The RDT is 0.1 centimeters per second. So in the end, what do I get there? It's 100 times 0.1. Oh, I think we've already gotten this answer today, haven't we? What do you get? 40 pi, but of course the units this time around, I think I want to actually say. What do the units come out to be? Centimeters cubed per second. Before you ever even did this problem, even before you wrote anything down, I think you would expect the answer to be something in centimeters cubed per second, because the thing that was asked for was a volume rate of change per time, right? So, that makes sense. And also the unit analysis actually confirms that, right? So 2 ways to get at the unit. 1, it should make sense. 2, the units actually should work. If you plug them in, they should actually get the right units. So again, I want to make sure we're emphasizing here, there are no approximations this time around. We're actually dealing with instantaneous rates of change. Notice the correct use of the actual equal sign at every point. We're talking about the instantaneous rates of change here. Okay? So everything works out very nicely here. And this is your first related rates problem. Okay? You just did a related rates problem. And by related rates, we mean you used an equation that relates rates. Right? That's all. Yeah. With 0.1, like t per, yeah, I think about that. Yeah, I'm trying to think. Maybe if it's constant rate, maybe, yeah. So we've already seen a little bit of this, but you'll see some of the things that will get highlighted in other problems too. I'll try to name those things as we go. This is somewhat on the front of that packet I just gave you. Maybe not. I don't know. I've kind of written it in my own way too. I don't know. You can kind of highlight the things that I've highlighted. So step 1 would be to easier said than done. Understand the problem. Just if you could just understand the problem, that'd be great. Similar to I told you, this is going to have a similar field optimization a little bit. I mean, you're going to have to come in with a little bit of pre-cop wrangling, right? You're going to have to be like, okay, size up the situation. Identify the variable whose rate of change you seek. You saw us do that on the previous slide, and the rate of change you know, and any other things you might know in the problem. Maybe give them helpful names, like we just did. Drawing a picture, just like in optimization problems, is often a great strategy to get in on these, and a lot of times also these have a geometric flavor too, I'll just say. This is an important thing that just didn't come up in the last problem, but it will in some problems we'll see soon here. Be sure to distinguish things that are changing from things that are not changing in the problem. Sometimes you'll be like lost at sea because you're like, I don't know which thing, what am I taking the derivative of? There are like 7 variables in this equation. Well, maybe they're not all variables. Maybe some of them are actually constants, right? So just take careful note of the things that are actually changing. You got a cylinder of water that's like emptying. The radius isn't changing. That's a constant throughout the whole problem, maybe, right? Whatever it might be. Take careful note of that. And this is the thing you just saw us do, right? Write an equation relating the variable whose rate of change you seek with the variable's rate of change you know. Oftentimes that's geometric. Like I said, could be the volume of a sphere. And then, and again, I don't know if are you writing all this? This is for the most part, I think even stolen fairly closely to those documents. It's pretty much word for word, right? I think I cut some things out and I highlighted certain things, so maybe you could like bust out your pink highlighter and like highlight the things that I've highlighted, I don't know, whatever you like to do. Okay? So don't be like trying to write every word down here. All that. It should be on the packet there. Did you get a packet? Okay, good. All right. So then step 4, of course, is what you just saw us do, and that's to differentiate both sides. And the word is implicitly, right? And by implicitly we mean chain rule, like everywhere, right? Chain rule, chain rule, chain rule. The chain rule is like your life now, isn't it? Yeah, I know. Okay. Keep in mind that we're almost always in all these problems. I'm trying to think if there's ever a time when we're not differentiating with respect to t. We're almost always talking about time here, right? Substitute values that any quantities that depend on time, and like I said, we need to. This one and the previous step that talked about things that change and things that don't change will become a little bit clearer as we do another example maybe here. But it's certainly true that, like I said, in the example where you might have a cylinder that's being depleted of water or something like that, that the radius doesn't ever change, it's constant, maybe, as in this particular problem. So that means if someone gives you the radius of this cylinder, that you would be welcome to plug that in right away as soon as you write it down, pre-calc style, before you take a derivative. The things that you can't plug in until after you've taken the derivative are the things that change, the things that depend on time, right? So that's just what that's saying. That's all. That's all. And then, of course, interpret the solution, make sure it makes sense in the problem, make sure you've actually answered what was asked, make sure you've used the appropriate units and kind of maybe done a little unit analysis to make sure it seems to be working out, et cetera, et cetera. And that's your easy 6-step process. Oh, is that all I have to do? Yeah, you got this. Okay. So let's do another one. This, I think now we are actually on script. Yes, that problem is right here. Looks nicer up here, but whatever. Yes? Okay, so what does it say? Assume the radius of the sphere is a differentiable function of t, and let v be the volume of the sphere. Find an equation that relates dv dt to dr dt. We already did that. I'll just copy it from above. What was it? dv dt equals 4 pi r squared dr dt. So C above work. I don't know why I have that. There you go. Okay. Let's do a more interesting problem here. I don't know why this was on here. Yeah, that's all. All right. Part B. Let's do a different problem here. This is interesting. We got like 3 things going on maybe. Sounds exciting. What we need maybe before we even get into this problem, assume the radius r and height h of a cone are differentiable functions of t. I think we're going to need, and let v be the volume, I think we're going to need the volume formula for a cone. By the way, yeah, which maybe you just know off the top of your head. I think yeah, there's like a 1/3 involved. Yeah, it does look like that. The cylinder formula, if I cover up the 1/3, that's the volume of a cylinder, yes? And so that's how I remember it. I always think of a cone or any pyramid that can be sort of described by a cylinder of the same radius and height, or the same base and same height for any polygonal pyramid, has the same volume as the cylinder divided by 3, right? Or the prism divided by 3. Does that ring a bell? Like this idea that, so it's a bigger idea. It doesn't just work for cones and cylinders. I don't know, did your geometry teacher talk to you about that? I think it's kind of fun to take the manipulative. If you have 3 like cones of water, you pour them in and fill the cylinder with 3 cones of water, fills the cylinder with the same radius and height. That all being said, I do actually think that on the AP test, they won't expect you to memorize these formula if you are required to use the volume of the sphere even in the problem. They'll provide that in the question. There's no formula sheet that applies to the whole test. But they don't give you any calculus formulas ever. But they might give you something like that. Good. Can you take the derivative of this, please? Keep in mind that R and H and V are all things that might depend on T. Which means, how do we take the derivative of some function times another function? You'll definitely need the chain rule somewhere, maybe. But you'll also maybe need you might need the product rule, since we have a product of things. Yes? Let me do the first part for you again. There you go.
Thanks. Oh my gosh.
Thanks, Mr.
You're welcome. Yeah, so how do we take the derivative of R squared H? That's the question, right? Or here, are you with me on this? That makes sense. You want to take a stab, someone? You guys are all so excited. I love it. Wait. Thanks for your honesty. Appreciate that. Okay, Jonathan wants in on this. Go ahead.
Alright, so it's 1/3 pi times h, no, 2rh.
2rh dr dt. Do you see what he did there? He held h as if it's constant and took the derivative of r squared with h coming along for the ride, right? That's the derivative of r squared times h. Yeah, so the derivative of the first times the second. Yeah? Keep going. You're not done, right?
R squared
Plus r squared dh dt. I'm going to just go ahead and agree with Jonathan. Okay? So do you see the product rule being used there? I hope you do, and you see that it's the correct application of it. Again, I like the language I just used too. I think you might want to get used to using. I don't know if you've ever thought about the product rule this way, but one way of saying the product rule is to think this is the derivative of this thing with h being considered constant, right? This is the derivative of this thing with r being considered a constant. Yes? Does that make sense? I mean, I'd like to start maybe thinking about the product rule in that way maybe. But regardless, it is a good use of the product rule. And that is the answer. The chain rule is required right here, but not really there, I mean, depending on how you think about it. You gentlemen. Okay. That's all that's asked there, right? All right, we got a hot air balloon problem. This looks like fun. Okay. Albert, read for us. Go. We got a hot air balloon problem. I want to hear all about it.
A hot air balloon. Excuse me. Excuse me. I'm reading the problem right now. Huh?
All right, guys.
A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff. At the moment the rangefinder's elevation is high over the floor, the angle is increasing at the rate of 0.14 degrees per minute. How fast is the balloon rising at that moment?
And unfortunately, they have all this, like, the solution kind of worked out for you. I don't love that. But, so we'll go with the picture they have there, and I think it makes sense that that is the picture we're trying to draw here. Do I have it somewhere? No. I guess I have to draw it. You have it on your paper, but I don't have it here. So we got this theta that's, again, let's think hard here about what's changing and what's not changing. So here's our balloon going up. We're using a rangefinder to sight the angle of the balloon as we go kind of maybe before we do too much else, let's try and give some names and like maybe write down the things we know, right? That's the kind of the idea here. 0.14 radians per minute, what would you like to call that? Yeah, how about d theta dt? And this would be like the current value of theta at the moment that we freeze the picture. And this, I don't have a name for it yet, but maybe I can label that in the picture. And what are we trying to find actually? How fast is the balloon rising? So what do you want to call that? The HDT. So just to go back over here and label some things in the picture, you got theta. Is that the letter they use, by the way, the Greek letter?
Yeah.
Theta. Okay. I just want to make sure All right. And do they use H too? I assume so. That seems like good names. So H. Okay. And we're asking, what is this vertical change? Looks like it'll be something positive. Okay. So where does the 500 fit in? Yeah, Rebecca.
It's the base.
Okay. And then I guess the other question is, which things are changing in this picture? The angle changes, true story. The height, anything else that changes? The hypotenuse changes if we wanted to keep track of it, though perhaps we don't. But if we wanted to, which by the way, would be equally good. I feel like there are other problems we do that we're like, you're letting out string on a kite. We got the same problem maybe. And like where someone cares about how fast the string is being let out along this. In this particular problem, I think we don't care about that, but it is true. If we cared about it, the hypotenuse would be something that is also changing. Is there anything not changing? The 500. So actually, we don't have to give it a variable name. It's not a variable, right? This is 500 feet. It will be. It always is. It is right now. Okay. Great. Can you give me something that relates the things we care about? Maybe something that relates theta and h and 500. And again, it's a little sad that it's like written there. Like imagine that it wasn't there and that you had this striking insight. What's the insight, Navesh? Genius. Tangent of theta. The tangent of theta, we realize that our precoc knowledge comes to the rescue here. We can realize that tan theta does relate h and 500 in the way that we desire. Perfect. Now you have two options here. You can differentiate it as it is here. Looks like they're making the suggestion to move the 500 over. I think I support that. I guess I just lost the feet there, but we'll just remember later in our lives that there's a foot there maybe. I don't know, whatever. Okay. So if you're ready to differentiate, it's a good thing we know the derivative of tangent. What is it, Grace? You're like, yeah, you love that one. Okay. 500 secant squared theta 08 times, yeah? Everybody, yeah, d theta dt. Chain rule, and the derivative of h with respect to t is just the h dt. And then I think we're in a good way right now, right? We know theta is at the current moment. We can now finally plug in. You understand what we mean now when we go back to those instructions earlier on? What are you allowed to plug in early on? Because it would be very tempting at the very beginning of this problem to be like, oh, well, we plug in this distance for 500. We plug in for theta. We plug in pi over 4 because that's what theta is. Whoa, hold up. If you do that, then when you go to take the derivative of tangent of pi over 4 is 0 because it's just a constant. So make sure that you're not substituting anything in. Is it okay to substitute 500 in at the beginning? 500 in at the beginning? Yes, because it's not something that changes. Is it okay to plug in pi over 4 for theta at the beginning? No, it's not okay, because that's something that does change. So that's that conversation. Anyway, so plug in the things you want and find the thing you need. dH/dt is what we want, so hopefully we'll get it here in a second. Pi over 4 is nice, isn't it? So that's cool. This is 0.14 per minute. Keep in mind that this is feet right there. Squeeze it in there. Okay. Secant of pi over 4, I gotta think this through. Cosine of pi over 4, I know that one. How about 1 over root 2, just for fun? Is that what, okay? I like it, because if I square it, I know I get. Or yeah, if I take the secant, I get root 2, and if I square that, I get 2. So I think it's 2 there. This thing is 2, which by the way means all this can be done pretty nicely without a calculator. Because 2 times they set us up for success, didn't they? 2 times 500 is a number I like. 1,000 times 0.14. I think I know how to multiply stuff by 1,000. So what do I get? 1, 4, 0. 1, 2, 3. What are the units? Feet per minute, if you kept track of all that in your scorecard. Which again makes sense for a reasonable set of units for the vertical change here, right? Here, you're really good with that. Don't make me back. Okay. We set up the police cruiser problem. This is an exciting chase scene. Okay.
Can you go back for a second?
I'll go back for a second. Who's excited about reading this? Steven, you look excited about reading about the highway chase. Go ahead.
Sure. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and now is moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. So if the cruiser is moving at 60 miles per hour as the instant measurement, what is the speed of the car?
Okay. Now again, they've destroyed this by actually writing all this stuff down. It's more fun if you do it. But then they've already labeled things in the picture too. Again, these are all. Well, I guess I should ask you, which things are changing this picture in terms of these variables, x, y, and z? And are any of them constant?
Is that a still picture or the moving picture?
I mean, you're going to watch this happen here. This car is going this way. This car is going this way. This is just one frozen frame. I think they're all changing. Yeah, right? So, and in fact, we're told that this side is changing. This is the radar gun measurement here, right? This is the distance between them he's measuring. Okay. So we should write these down. I'll write them down too. They're in your thing. But let's write some of these things. The thing we seek is, what's the speed of the car? Of course, that's what we seek. What is that called? dx dt. In the picture, we want to know how fast that side length is changing. By the way, we expected, I think, to be some positive quantity, don't we? Maybe measured in miles per hour. What is dy dt? Is that given? 60. Except, yeah, do you see that we might want to consider that to be negative because is that side length decreasing? I think it is, right? So decreasing to me means the negative derivative. Z, do we know anything about z? dz dt, what is that? 20 miles per hour, positive. And at the very moment that we're interested in talking about all this, we are, y is equal to, didn't they give us y? 0.6. And the car is 0.8 miles to the east. Now, I don't know how we know that, but we'll just go with it. Well, actually, no, maybe we do know that. Maybe because there's some landmark here or something. We know that's 0.8 miles. Caught a lot of people at this corner. That's 0.8 miles down there. I don't know how they know that. Could we know z? Could we know z if we wanted to know z? It's not given, but actually I think I might know it off the top of my head if I know my Pythagorean triples. It happens to be 1. Work it out though if you don't believe us. Yeah, 6, 8, 10 is the. But you can work it out too, right? What is it? Z will equal the square root of x squared plus y squared. So work it out as 2.6 squared plus 0.8 squared. And see that you get 1. Okay. Try it. Good, cool. We're doing well on this problem. Do we have an equation? We still don't actually have an equation anywhere. Well, actually, we kind of just did. We do, right? It says on the paper, too. We actually just realized, we all just realized, that the thing that relates the pre-calc style variables is just the Pythagorean theorem, in fact. And to get a related rates equation, to get this to calculus apply this, just take some derivatives with respect to time everywhere. And then you'll get an equation that relates all 6 of the quantities we have either known or unknown. There's only one unknown here. So we get what is the derivative of x squared? Well, it's 2x dx dt plus 2y dy dt equals 2z dz dt. And the thing we want is dx dt. Plug in all the things you know here. There are 5 of them, and the one thing you don't know will be the only unknown to solve for. You'll actually have to solve for it, won't you? All right, did I mention that we're doing this over 2 days? Yes. So today and tomorrow, we're doing related rates. The homework tonight is to do the odd numbered ones in this packet. The homework tomorrow night will be, of course, to do the even
Kimball
numbers.
Tyler,
And
please come
please
to the
make a
main
note
office.
that all
Kimball Tyler,
the
please come
answers
to the
are on
main
the back.
office. Auditions for the
On the very
top
last
20
problem.
contestants for
Okay.
RM Idol, Richard Montgomery's annual singing competition, will be held Wednesday, November 16th after school at 262 and Thursday during lunch in the school break. Please sign up for an audition slot. Sign up sheets are located outside of 262.
Certainly she has a
Everyone get it? Odds tonight.